Next topic: TriDiagonal-Matrix Algorithm. The solution of discretization equations like 2.72 for one-dimensional situation can be obtained by the standard Gaussian elimination method. Because of the particularly simple form of the equations, the elimination process turns into a convenient algorithm. This is sometimes called the Thomas algorithm or the TDMA, TriDiagonal-Matrix Algorithm. The designation TDMI refers to the fact that when the matrix of coefficients of this equation is written, all the non-zero coefficients align themselves along three diagonals of the matrix. For convenience in presenting the algorithm, it is necessary to use somewhat different nomenclature. Suppose the grid points were numbered 1, 2, 3 till n, capital N, with points 1 and n denoting the boundary points. The discretization equations can be written as A I phi I is equal to B I phi sub I plus 1 plus C I phi sub I minus 1 plus di, where I is equal to 1, 2, etc. n minus 1, capital N. Thus, the function phi I is related to the neighboring functions phi I plus 1 and phi I minus 1. To account for the special form of the boundary point equation, let us set C1 is equal to 0, B capital N is equal to 0, 2, so that the functions phi 0 and phi sub n plus 1 will not have any meaningful role to play. When the function boundary values are given, these boundary points equations take a rather trivial form. For example, if phi 1 is given, we have the following: A1 is equal to identity, B1 is equal to 0, C1 is equal to 0, 2, D1 is equal to phi sub 1. These conditions imply that phi 1 is known in terms of phi 2. The equation for I equals 2 is a relation between phi 1, phi 2 and phi 3. But since phi 1 can be expressed in terms of phi 2, this relation reduces to a relation between phi 2 and phi 3. In other words, phi 2 can be expressed in terms of phi 3. This process of substitution can be continued until phi sub n is formally expressed in terms of phi sub n plus 1. But because phi n plus 1 has no meaningful existence, we actually obtain the numerical value of phi sub n at this stage. This enables us to begin the back substitution process, in which phi sub n minus 1 is obtained from phi sub n. Then phi n minus 2 from phi sub n minus 1. And so on, phi 2 from phi 3 and phi 1 from phi 2. This is the essence of the TDMA. Suppose in the forward substitution process we seek a relation phi 1 is equal to capital P I, phi sub I plus 1 plus Q I. We obtained it after we have just obtained the following: phi sub I minus 1 is equal to capital P I minus 1 phi 1 plus Q sub I minus 1. Substitution of equation 2.77 into equation 2.74 leads to the following expression: phi 1 is equal to Bi over Ai minus Ci capital P sub I minus 1 phi I plus 1 plus Ci capital Q sub I minus 1 plus D sub I over the same expression Ai minus Ci capital P sub I minus 1. This expression can be rearranged to look like equation 2.76. In other words, the coefficients capital Pi and Qi then stand for the following expressions. I will not repeat them. They are the same as in the formula 2.78. This is P I and this is capital Q I. These are recurrence relations since they give capital P and capital Q I in terms of P sub I minus 1 and Q I minus 1. To start the recurrence process, we note that equation 274 for I is equal to identity is almost of the form 2.76. Thus the values of P1 and Q1 1 are given by the following expression: P1 is equal to B1 over A1, Q1 is equal to D1 over A1. At the other end of the Pi and Qi sequences, we note that B sub n is equal to 0. This leads to the following: P n is equal to 0, and hence from equation 2.76 we obtain the following: Q sub n is equal to phi sub n. Now we are in position to start the back substitution via equation 2.76. Now let's make the summary of the algorithm. First, we'll calculate P1 and Q1 from equation 2.80. Second, use the recurrence relations 2.79. We obtain P m Qm for P I and Qi for I is equal to 2, 3, and so on till capital N. The third step, we set Qn is equal to phi n. And the last, fourth step is we use equation 2.76 for I is equal to capital N minus 1, comma, N minus 2, comma, so on, 3, 2, 1, to obtain phi n minus 1, phi n minus 2, since till phi 3, phi 2, phi 1. The TriDiagonal-Matrix algorithm is a very powerful and convenient equation solver whenever the algebraic equations can be represented in the form of the equation 2.74. Unlike general matrix methods, the TDMI requires computer storage and computer time proportional only to capital N, rather than to n to the second power or n to the third power.